Okay, I'm going to talk about tandem queues again, like Jose did. I did not know he was going to talk about a so closely related topic, but that will give me a chance to save a few minutes by skipping some introductory things. Does it work? Yeah? Okay, good. So, the outline of my talk, I'll briefly sketch the problem. Again, the two-node tandem queue. There have been some previous solutions for efficiently simulating that queue. I'll briefly discuss those and point out one, disadvantage they have. Then I'll introduce our approach, compare our approach to those previous ones, in particular in light of that particular problem that I'll mention in a moment. And finally, I'll discuss the performance of our approach. So, we have the problem of the tandem queue, and this will not be much new given what you've already seen from Jose. So we simulate two queues in tandem, arrivals at the first queue with rate lambda, service rate at the first queue mu1, service rate at the second queue mu2. I call the number of customers in the first queue n1, Jose called it x1, but it's the same. N2 is for the second queue. Again, I assume that the three rates sum up to 1, which is convenient because then they can be interpreted simply as transition probabilities in a discrete time Markov chain, which is sketched down here. Horizontal axis, the number of customers in the first, vertical axis, number of customers in the second queue. And in every state you have a transition corresponding to an arrival in the first queue, to a service completion at the first queue, and to a service completion at the second queue. And the quantity we are interested in is the probability that if you start basically here, so after the first arrival, the probability of hitting one of those states in which the sum of the contents of the total of the two queues exceeds some value which I happen to call large K, Jose called it N, before returning to the empty state. So basically the probability that a busy cycle reaches one of those overflow states. That probability is small if the queues are stable, and they are because I've assumed that the arrival rate is less than even the lowest of the two service rates. So we need some kind of rare event simulation. I will only discuss importance sampling. I will not discuss splitting. And very briefly, importance sampling means you run your simulator under different change of measures. So basically, you change the probabilities, the transition probabilities of the Markov chain. And then you count how many times out of, say, n simulations you actually reach the overflow state. And each of those indicators you weigh by a likelihood ratio L, the likelihood ratio of the ith sample path, basically telling you the ratio between the probability of that sample path under the original measure, so the real lambda mu1 and mu2, and the modified system. So that's the situation we're going to look at. The trick then is to find a new set of transition probabilities for your Markov chain such that you get a good estimator. The first result, Jose mentioned it, is from Pieter-Tjerk de Boer from 1989. They said, exchange the arrival rate and the bottleneck service rate, in this case the service rate of the second queue, and do that everywhere in the state space. So everywhere replace the lambda and the mu2, and then you have your new measure to simulate under. It's inspired by large deviation theory, but unfortunately it does not work well for all combinations of parameters. In particular, when mu1 and mu2 get close, you have problems. Again, as Jose pointed out, because on this set of states, those stats will have a very large contribution to the likelihood ratio, and thus cause a large variance of your estimator under some conditions. So it doesn't work well everywhere. Another change of measure, basically that says that this Pieter-Tjerk de Boer change of measure is fine in most of the state space, but not on the boundary. You should have a different change of measure on the boundary. And then the trick is, what to do on that boundary and how to connect the two. One suggestion for that was given by Zabunenko and Nicola about 2005. They said, we can come up with a good change of measure on this boundary, namely replacing the arrival rate and the first service rate, so the service rate in the first queue, even though it's not a bottleneck one. And as we move away from this boundary, we linearly transition to the Pieter-Tjerk de Boer change of measure. As sketched in this graph, on the horizontal axis we have N2, that's the number of customers in the second queue, so that's the vertical axis in this plot. And you see that linearly, the new service rate, the service rate of the second queue in the modified system, linearly changes from one value to another value, and then beyond this point it's just the Waregem-Walrand change of measure. Yeah, so at this boundary we have one change of measure, in the interior we have something else, and there's a linear transition between the two. Experimentally they show that it works fine, but unfortunately they have not yet been able to prove that it's asymptotically efficient everywhere. And there's a problem. How do you choose the width of this boundary zone? I just sketched it here with a width of 5, but of course it's just a free parameter. You could also choose, say, 4 or 6 or 10 or whatever. The only guidance they give is, well, try a couple of values, and they found that for this particular set of values that 5 was a good width of the boundary. It gave the lowest variance, but they don't have an explicit formula, for example, for giving that parameter. So they have a parameter in their change of measure which is not really clear how to choose it. Then there's another change of measure mentioned by José, the one that was derived by Dupuy, Sezo and Wang in 2007. There's a whole background behind it, how they derived it, but in the end effect they also have a change of measure which gradually changes from one thing on this problematic boundary to something else in the interior. There's a whole bit of math in between, but if you make a plot of it, then it turns out to be some kind of smooth function showing again, say for example, the new surface rate at the second Q gradually changing from one value at the boundary to another value in the interior. Nicely, they can prove that it's asymptotically efficient, but in a sense this change of measure has the same problem because it also has free parameters that still need to be chosen. One of them called epsilon, which kind of determines how steeply this crossover is, whether you go more like this or more like this. And there's another parameter, delta, which basically determines the width of this changeover interval. Nicely, their asymptotic efficiency proof works for a very large number of possibilities of choices for epsilon and delta. They only need to go smoothly and quickly enough to 0 and so on. They have a few nice limit conditions on them, but that's all. And under all those conditions, it's asymptotically efficient. That's of course very nice, but still one wonders, well, what is a good choice? So we see that there are two changes of measure which seem to work well. Both have a gradual change from one to another change of measure, and both leave some parameters open regarding how quick that change should be. So the question arises, can we find something more about that? Can we find out what the optimum would be? Well, it's known that for important sampling there's always a change of measure which gives 0 variance. Well, that change of measure obviously must have exactly the right change from one to the other. But it's impossible to compute. Basically, if you can compute the 0 variance change of measure, then you no longer need to do your simulation. But perhaps we can approximate it analytically. Well, that's a question, and it turns out that yes, we can do that. The great mathematician Obama. So how do we do that? We define P of n1 and 2 as the probability of reaching our overflow state before emptying, not necessarily starting in the starting state that I pointed out at the beginning, but in the starting state n1 and 2. So it's basically a function which gives me from any point in the state space the probability of reaching overflow. Of course, I can't compute this function. If I could, then I could immediately compute the 0 variance change of measure and I'd be done. But at least I can write down the equations governing this probability. It's quite easy. For example, P starting in this point equals just deconditioning on the 3 possible transitions, lambda times the probability of reaching overflow from this point, plus mu1 times the probability of reaching the overflow from this point, plus mu2 times the probability of reaching overflow from that point. Now that gives me a set of equations for this P n1 and 2, which holds in the interior. I get a slightly different equation here on this boundary, and I get yet another equation on this boundary. Why? Well, because in these boundaries, one transition is missing. Yeah, you can't have a departure from an empty Q. And I get some boundary conditions over here, and that the overflows. Well, and the next step is solve them, but as I said, that's not possible, so slightly less, solve them approximately. Which is not trivial either, but we can at least try something. And just by trying some possible solutions, I came up with this approximation. I now put a little tilde above to indicate that it's just an approximation. The first part is just an exponential decay in the total population of the two Qs. That's basically the result suggested by large deviation theory. And it turns out that if you add this extra term, then you get an approximation which not only satisfies these equations in the interior of the state space, but also on this boundary. Unfortunately, not on this boundary. So that's an approximation to the real P tilde. And since this boundary was the problematic one, perhaps basing my change of measure on this approximation will give me a good estimator. So what we do, we pretend that this is actually the real expression for P in 1 and 2, plug it into the equations which go from the real overflow probability to the new transition probabilities from a Markov chain. That would give a zero variance change of measure if I had actually the real probability there, which gives me this set of equations. The new arrival rate should be equal to mu2, the new service rate at the first Q should be the original service rate at the first Q times something complicated. I'll get back to that one later on. And a similar expression for the service rate in the second Q. Well, I showed you graphs of Nikolai and Sabunenko's change of measure and of Dupree's change of measure. So let me also show you a graph of this thing. Well, again, we see a smooth transition from N2 is 0, so from the bottom over here, to something else in the interior of the state space, so basically in that area. And it's a smooth transition. And there are no parameters left. Now look at the equation. There's lambda mu1 alpha, which is just expressed in terms of the rates. There are no free parameters to choose anymore, in contrast to the other changes of measure. Let's compare them with the two change of measures that we've seen before. First with one from Sabunenko and Nikolai, the one that had a linear change of measure. I chose their boundary with their transition zone with 5 because in their paper they indicate that that's the optimal value they found, and well, it matches quite nicely. Yeah, there's perhaps a small difference here, but the difference is not too large, so one cannot wonder that this works well. Next, let's take the change of measure from Dupree and his co-authors. Well, that looks like a very nice match. But of course, I played with epsilon and delta to make it match this nicely. However, in the change of measure from Dupree, the transition zone, the width of the transition zone has to increase as the overflow level K increases. So as you look at asymptotic regimes. So this may be correct, or maybe the optimum or whatever for a specific overflow level, but as I increase the overflow level, it starts to run away. Yeah? Because the change of measure, the asymptotic efficiency proof, it only holds if you let the width of their transition zone increase sufficiently slowly, sufficiently fastly with the overflow level. So for some parameters it may fit nicely, but actually it runs away. Still, of course, their change of measure is provably efficient, provably asymptotically efficient. So although it deviates quite strongly from what one would expect analytically, it still works well. Now, how wide is this transition zone? Yeah, how wide is this? I've again written down here the equation that I derived, the equation in this case for the new service rate at the second Q. It consists of the original arrival rate multiplied by this thing. And you see here in the denominator and in the numerator two terms which are basically competing. For large values of N2, so when you're in the interior of the state space, well, this is a lambda over mu1, which is less than 1, so a thing less than 1 taken to some high power means this term will vanish, and in that case it just becomes 1 over 1 times lambda, which means that mu2 tilde indeed goes to lambda. On the other hand, for small values of N2, this term and this term may dominate, and that then mainly depends on how big this alpha is, whether this term gets a chance to dominate. Alpha has this form, it's mu2 minus lambda divided by mu1 minus mu2, and in order for this thing to get a chance to dominate, alpha should be big. How can we make alpha big? By having the denominator go to 0. Which basically means that in order for this thing to be big, mu1 must be close to mu2, and because here the n2 is in the exponent, the width of this transition zone is of the order minus the logarithm of the difference between the two mu's. And that's independent of the overflow level. So we have a change of measure here, calculated this way, but we still don't know whether it works well. Let's try it. I ran a couple of simulations. I took here a couple of cases where, in this case, mu1 and mu2 are very close together, just to stress test the thing. I chose several overflow levels. There's an estimate coming out, which I checked is correct according to a numerical calculation, and we even see the relative error decreasing as the overflow level increases. So that's quite a good estimator. I took another point. Unfortunately, there the relative error slowly increases, and it's a bit suspicious. I mean, perhaps it will converge, it's somewhat unclear. So further study is needed. Then I studied it another way, and that's this plot. This plot is the state space. This plot is in the parameter space. On the horizontal axis we have the surface rate of the first queue. On the vertical axis the surface rate of the second queue. And because we assume that lambda mu1 and mu2 sum up to 1, that also fixes lambda. And in a grid here I did a numerical calculation of, well, the overflow probability and the variance of my estimator. One can compute that numerically rather than by doing the actual simulation. And by doing that for a couple of overflow levels, I let my computer give it a color depending on whether the relative error started to become constant. In that case I made it green. Seemed to grow exponentially fast in the overflow level, then I made it blue. Whether there seemed to be infinite variance, well, that happened nowhere, but then it became red. And unfortunately my computer warned me that here I had some problems inverting matrices that were needed for this calculation. So I made those points black because I can't draw a conclusion there. This looks very promising. One thinks, oh, okay, this is green everywhere. It's slightly bluish here, but I suspect that that would go away if I would do my calculations at an even higher overflow level. So based on this, I think, okay, this looks like a change of measure which actually might be asymptotically efficient everywhere. So we spent a lot of work on trying to prove this, and it didn't work. We couldn't manage to get it to prove. And at some point we decided to say, okay, perhaps then it's not asymptotically efficient. Let's try the opposite. Let's try to prove, for example, that it has infinite variance somewhere. How do you prove infinite variance? Well, one way is to use a criterion that was published by Randava and Junaja a couple of years ago. And they say, well, if in your state space you can pinpoint a couple of cycles and compute the probability of such a cycle and the likelihood ratio contribution of that cycle, and the sum over this set of cycles exceeds 1, well, with some technical conditions, if that is the case, then the variance of your estimator is actually infinite. Now, due to the way I constructed our estimator, we do not have bad likelihood ratio contributions on this axis, nor in the interior. The only place where bad likelihood ratio contributions occur is on the vertical axis. So we tried to sum up over a couple of cycles along this vertical axis, and well, we couldn't get it to exceed 1. So then I decided, okay, I'll write a computer program that just sums over thousands of these cycles and see whether it exceeds 1. I have here a curve. The first curve is over cycles up to length 3, up to length 6, up to length 9, up to length 21, and then all of a sudden it exceeds 1. So for some values of the parameters, namely mu1 and mu2, roughly equal to 0.42, actually there is infinite variance, which somehow did not show up in my nice picture, because it's really a limit result. It's really exactly at this boundary where I didn't take any samples, because I can only sample in a grid and not everywhere. So what do we have? We have a new change of parameter of measure for tandem queues, at least for a 2-node tandem queue. It does not have any free parameter and thus gives some insight into what actually the width of that change interval should be. It works fine, asymptotically efficient, apparently in almost the entire parameter space, but not everywhere. Which of course immediately points to possible future work. This observation is only done numerically so far, so it would still be nice to find analytical proof of the asymptotic efficiency or proof of the region where it's infinite variance, etc. So analytical proofs or bounds for the efficiency would be an obvious next step. Furthermore, of course, it does have this problem at mu1 very close to mu2, so another obvious step would be to try to repair it. In fact, the Dupree change of measure also has a separate treatment of the area near the origin. Perhaps a similar treatment would work here. Or, in the approximation that I calculated for my p, I showed only one term here, but actually I have a second term, which initially I ignored because it seemed to work fine with just one term. Perhaps that second term is just what is needed to repair that. This idea was so new that I couldn't try it before today. And of course, well, a 2-node tandem queue is nice. It's a well-known benchmark example, as this morning has evidently shown. But it's not the most interesting case for practical applications. So trying to generalize this to other models would be also an obvious future piece of work. Thank you for your attention.
One question. The experimental performance you have shown,
Yeah.
was it on the small samples or on large samples? You have taken two cases.
Yeah.
One is performance experimental, another performance numerical. Oh yes.
This one, you mean?
So this was taken on large samples or on
Here it 10 to the
small
power
samples?
8 replication, so quite a lot of samples for that specific case. Yeah. Any other questions?
Well, it seems not to be the case. I'm sorry if I have rushed you, but the fact is that to keep this schedule for the lunch, it is important that we start the next session sharp. That means at 11:15. So please be back in time, both the speaker, of course, and the audience. But thanks anyway to you and all the speakers for this.